Hi everyone, I'm Jain, a fifth year PhD student at UC San Diego with Professor Dinesh Bharadia. In this talk, I will describe a very fundamental problem in today's multi-user millimeter wave network and how we solve it through our flexible directional frequency multiplexing. So millimeter wave in the next generation millimeter wave network is envisioned to support many applications such as autonomous vehicles, augmented or virtual reality for an immersive experience, and it has already revolutionized the gaming, healthcare, and education industry. All these applications require sending large amount of data through the network, so they need a high throughput link. These applications also require low latency. For example, if we don't deliver low latency to a VR device, then the video might freeze or stall. In addition, there are multiple devices that need to be supported with the network. So the network has to be scalable and provide high throughput and low latency to all these devices. Does today millimeter wave network meets these requirements? Turns out, millimeter wave system meet only the throughput requirement thanks to the high bandwidth, but they fail to provide low latency and scalability. Why is this? So it is because millimeter wave uses highly directional beam to combat path loss at these frequencies, and this very existence of narrow beam impose restrictions on latency and scalability. Let's see how. Consider a system where we use millimeter wave to serve these users. Now, because it's a very narrow pencil beam, we serve only one user at a time in a TDMA fashion, while other users have to wait for their turn. In this example, we serve user 1 in time slot 1, then user 2 in time slot 2, then user 3 in the third time slot, and so on. So this occurs high latency when we have many users in the network. Also, when the base stations serve one direction at a time, each device gets a lot of instantaneous bandwidth, which it may not utilize due to limited demand. But because these pencil beams, the base station cannot direct the remaining frequency resources to other direction. And so these resources are wasted. The other users could have used these wasted band, but they can't do that because these narrow beams are not pointed to them at that time. And therefore, despite high bandwidth, millimeter wave systems fail to meet the latency and scalability requirements. So how do we deliver low latency and scalability with directional beams? We develop a system called mmFlexible, which provides a flexible allocation of time and frequency resources to multiple users. For instance, we can serve 3 users in the first time slot using 3 consecutive frequency bands. Then we can serve other 2 users in the next time slot. In this way, mmFlexible provide low latency because now we are serving multiple users at once, and at the same time, it provides more useful resources to serve many more users, thus providing low latency and scalable millimeter wave system. However, building this system is extremely challenging. Let's understand it through a simple example. Consider the first time slot. Here we take the entire system bandwidth and we divide it into 3 contiguous frequency band and distribute these band to 3 users. So frequency band 1 is delivered to user 1, frequencies in band 2 delivers to user 2, and band 3 goes to user 3 in a frequency multiplexing or FDMA fashion. But to serve these 3 concurrent users, we need 3 concurrent beams. Creating concurrent beam is challenging Let's say if we naively split the single beam into 3 beams, then we lose power per beam. So assuming the system has the same total power available, then this power will be divided into 3 beams. Now, so each user will receive only a small power, which may lead to low throughput and low coverage. In mmFlexible, we aim to create 3 concurrent beams while maintaining high throughput to each user. So at one glance, it looks counterintuitive, right? How can we create high power beams to each user without pumping any extra power into the system? So for this, we need to think something out of the box. We are taught in school that beam pattern is a distribution of power in space or the direction axis. But actually the power is distributed not only along the space, but also along the frequency axis. So in the single beam case, the beam is narrow in space, but it is spread across the entire spectrum. Even in conventional split antenna case, each beam is narrow in space, but spread across entire spectrum. The problem is, if each user is served with only a small fraction of bandwidth, then the power is wasted in the rest of the frequency bands. mmFlexible utilizes this wasted power and it redistributes the total power in a way that power is maximized in the frequency band allocated to the user and minimized elsewhere. So basically, by this careful redistribution of power, we create concurrent beams where each beam is localized along both direction as well as along frequency. And in this way, mmFlexible delivers high SNR and high throughput link to every user. So the key features and contributions of mmFlexible that I will cover in this rest of the talk is how does it create these flexible concurrent beams for every user. I will also talk about a new hardware architecture that we developed to deliver these concurrent beams. And finally, provide a real-time solution to configure these concurrent beams in our hardware. mmFlexible provides flexible concurrent beams. And what I mean by this flexibility is that it supports any number of beams with narrow beam width. These beams can be in any arbitrary directions and support arbitrary beam bandwidth. Here, I define beam bandwidth as a fraction of system bandwidth that is allocated to the user, which is served by that beam. So how do we truly enable such flexible concurrent beams? We know that traditional phased array hardware is not capable of delivering such beam. So we need to design a new hardware. To deliver flexible concurrent beam, we propose a new programmable hardware, which we call delay phased array or DPA. Our DPA consists of a single RF chain that connects to an antenna array. This antenna array has a series of programmable delay element and programmable phase element. And we show that together, these delay and phase element can produce any flexible concurrent beams. So how does it work? To understand our DPA structure, let's consider a simple example of two antennas. Now DPA has two basic components, the phase component and the delay component. Let's see how individually they contribute to the frequency space response. The phase array programs a relative phase of phi, which controls the beam direction, which means we have a line in this frequency space plot and we can move this line along x-axis by programming the phase phi. The delay element produces a frequency-dependent phase of 2 pi f tau. So by programming different delay tau, we give a slope to this line, and we can control this slope, or we can give a different slope by setting a different value of tau. Delay phased array uses both delay and phase element to create a relative phase of 2 pi f tau plus phi. So it can create a frequency space plot which has a line with an arbitrary slope and an arbitrary x-intercept along the direction axis. Now, these frequency space plots are some kind of signature images or building blocks to create our arbitrary and flexible concurrent beams. How do we do that? Let's say we want to create this two-beam pattern. This pattern looks very different from the building block signature images we just saw. While the signature images had a linear pattern, this pattern is highly non-linear. As you can see, there is a sharp null between the two beams. It is not just a straight line in frequency space plot. So how do we create this non-linear pattern from linear building blocks that are created from our delay phased array? Let's understand this through an example of 3 antennas. The first 2 antennas contribute a signature frequency space image which has a positive slope. And the second and third antenna contribute a signature frequency image with a negative slope. By combining these two frequency space images, we can achieve our desired pattern with a null in between the two beams and high power in the desired angles and frequency bands. This response with just 3 antennas may look little blurry. So if we have more antennas, then we can create sharp and narrow beams. And you can see these patterns look very similar to what we want to create. So the final piece of puzzle is to configure delay phased array in real time. For this, we need to estimate the delay and phase values that gives our desired response. We formulated it as an optimization problem and we solved it to a closed form. So configuring DPA is as simple as plugging the desired beam angles, beam bandwidth to our formula, and this formula will give us the corresponding delay and phase values. Here, we show a simplified formula for 2 beam case, but we have derived it for any arbitrary number of beams, their beam directions or beam bandwidth. So please refer to our paper on our webpage for this generalized formula and derivation. This closed form expression provides valuable insight in designing our hardware. The time element is generally implemented using variable length transmission line on a circuit board, and building large delay lines on an IC at millimeter wave frequencies is prohibitive because of large size, bandwidth, and matching constraints. Our design ensures that we don't require large delays. As you can see, the delays are bounded by 3/2 beam. And because of this bounded nature of the delay, independent of the number of antennas, we can build our DPA hardware. It is feasible and it is scalable to large arrays. So we go back to our requirements and ask how flexible is our DPA. DPA can support any number of concurrent beams as long as we have enough antennas, at least more than number of beams. It can support arbitrary beam directions as long as these directions are separated by half power beam width. And anyways, if 2 users are located very close to each other, then 1 beam is enough to serve both concurrently. Finally, DPA supports any arbitrary beam bandwidth, and sometimes we may need only a small fraction of bandwidth for one user and the rest bandwidth for the other users. So how small bandwidth can we support per user? We empirically show that it should be at least 20% of the system bandwidth for a 2-beam case. Now, this limitation can be easily overcome when we have more beams. As you can see, when we have 16 beams, then those beams can carry as small as 5% of the system bandwidth. This is how a small beam bandwidth can be. There is no limitation on how large beam bandwidth can be. And this demonstrates that mmFlexible can support flexible concurrent beams. We evaluate mmFlexible through simulation as well as trace-driven emulation. Here is our test setup. We collect mmWave channel data in different scenarios and replay this data with our MacLayer simulator to evaluate our work and compare it against baselines. We show that mmFlexible is more flexible than other baseline. The traditional single beam system serves only one user at a time in a TDMA fashion, and it doesn't create concurrent beams. The split antenna system can create concurrent beam, but it compromises beamforming gain or SNR per beam. Recently, a new class of work has emerged called Rainbow Link, which uses true time delay array to create frequency dependent patterns. And this work produces a beam pattern that spread all frequency in all directions, like a rainbow. But it is not flexible for a multi-user network. Here, each user receives only a tiny fraction of bandwidth, which is not enough to meet their demand. And at the same time, a lot of power is wasted in other directions where there are no active users. So finally, we show that mmFlexible is the most flexible system to create concurrent beam with high beamforming gain and arbitrary high beam bandwidth. And this flexibility translates into our end-to-end results as well. Here we compare end-to-end latency and with 3 baselines, the TDMA, single beam, split antenna, and rainbow link. mmFlexible achieves overall 60 to 150% reduction in latency, while also providing 4 times better throughput than these baseline. These improvements are thanks to our flexible way of allocating time frequency resources in a multi-user mmWave network. For more results, please check out our paper. So this concludes my talk. I would emphasize that mmFlexible is open source. The code and the dataset is available on our webpage. Please check them out. Thank you for listening, and I will take questions.